Golang project is actually the compiler for Go language. So today I will introduce the two debug tools I enabled on Go for ARM platform. Okay, let's start. Okay. This is my agenda. It consists of two parts, TSan and MSan. For each one of them, I will introduce what is it and the algorithm implementing it. And also, I will introduce how to enable it on Go. And finally, I will give you a simple demo. Okay. As we know, the use of uninitialized memory is such an issue that is very difficult to reproduce and debug. So actually, MemorySanitizer, MSan for short, is developed to address that issue. And MSan is a dynamic tool which detects the use of uninitialized memory in C. And this tool relies on the bitprecise shared memory and also relies on the shared memory propagation. Bitprecise shared memory means that MSan can track uninitialized bits in bit field. And the shared propagation technique will tolerate the copying of uninitialized memory and also simple logic and arithmetic operation with it. And with shared memory propagation technique, MSan can avoid the false positive report on copying of uninitialized memory. Okay, shared memory. As the diagram on the left side shows, the application is located in the higher memory, and the shared memory is located in the lower memory. They have a one-to-one bit mapping relationship, and it means that each one bit in shared memory stands for whether the corresponding application memory is initialized or not. And 1 means uninitialized, 0 means initialized. And also, it's efficient to calculate the shared memory address corresponding to application memory by using bitwise and operation. Okay. Shared propagation. Actually, there are two kinds of shared propagation. One is exact propagation, and another is approximate propagation. And the basic shared propagation rules on the left side are all the exact propagation. They are load operation, store operation, as well as some bitwise operation. And it's not always efficient to make exact propagation. Take the integer addition, for example. The uninitialized bits in lower digit can affect any number of bits of the result due to the possible carryover. So it is difficult to model integer addition behavior. So we just use the approximate propagation to model this behavior. Here, we just use bitwise OR operation to model integer addition behavior. Apart from addition operation and some other operation like multiplication, comparison is also approximate propagation. What I talk about is the basic knowledge about MSan algorithm. Next, I will talk about the implementation I enabled MSan in Go. Before that, I will try to explain why Go lead the MSan. Actually, MSan does not apply to pure Go because the memory in pure Go is all initialized. But in Go, Go can call C function by the way called CGO. People can use the CGO to pass memory back and forth between C and Go. So if C create an uninitialized memory and passed it to Go, Go filled it in and returned it back to C. C code will not be aware of this initialization. So the false positive report will be reported. So to avoid these false positive reports, we need to instrument MSan in Go. Okay. This is MSan framework in Go. MSan library at the bottom implements MSan algorithm and provide the basic utility function. And all the memory access through runtime are intercepted by MSan library. With this implementation of this framework, the false positive caused by memory pass between C and Go would not happen. Okay. There are two special instrumentation I'd like to mention. One is the instrumentation of singular handler to trace the state and print the warning when use of uninitialized memory occurs. Singular handler also should be intercepted by MSan library. And another is about mmap. When MSan is enabled, the mmap call will be intercepted and the returning memory will be marked as initialized. Okay, I will show the simple demo for MSan use in Go. The code on the left side is the C code, and the code on the right side is Go code. The first line of the Go code is to make an array A, which is initialized, and then Go will call the C function named F, and in this C function, it will malloc an uninitialized memory and copy the uninitialized memory to array A. This is to say that function F will make the array A uninitialized. And then in Go code, it will initialize the fourth element of array A. And then Go code continue to call another C code named G. In this function, it will take code branch depending on the fifth element in array A, which is uninitialized. So actually, it's exactly the use of uninitialized memory. Okay, let's compare it in Go. The command line in blue shows the build command line. The compiler option MSan means that Go compiler will instrument MSan into Go application. The screenshot, maybe you can see that clearly. The message in red is reporting the warning that the use of uninitialized value here. Okay, that's what I talk for MSan. So next, I will introduce another debug tools, ThreadSanitizer. ThreadSanitizer, TSan for short, is developed to address the date race issue. Date race is that two concurrent access to a shared location, at least one of them for writing. It is kind of threading bugs. And also, it is hard to reproduce and debug. TSan is also a dynamic tool to detect the date race. It is also a sub-project of LLVM. In the algorithm of TSan, it will observe following events generated by a running program: memory access events and synchronization events. For memory access events, it will record the read events and write events. For synchronization events, TSan algorithm will record the local events, log event, and happen-before event. Okay. TSan uses an algorithm called hybrid state machine to detect the date race. The algorithm includes two state machines. One is global state machine. This global state is used to record the information about synchronization event that have been observed before. Per ID state records the information about each memory location of running program. TSan used these two state machines together to detect date race. Okay. This is the TSan algorithm. It seems complicated. I'm not going to explain this algorithm one line by one line. I just describe it briefly. When memory access event happens, TSan will scan all the memory access events that happening to same memory before to see if there is any one memory access event that has not happened before relationship against current one. if there is one and one of them is for writing event, that would be date race. That's what the algorithm wants to say in this slide. Okay, let's talk about what did I do in TSan runtime library to enable TSan on ARM. TSan library as a runtime library is implemented in compiler RT, which is also a sub-project of LLVM project. Because TSan requires specific memory layout to enable TSan algorithm. And we know the memory layout is also ARC related. So in order to support TSan on ARM, we should add memory mapping code for ARM in TSan library. So I'm not going to talking about the implementation of the mapping. It's ARC related and quite explicit to understand. TSan library provides some APIs that used to record all kinds of events to such as memory access events. This APIs list on this slide is the APIs for memory access. And this APIs list here is related to atomic operation. They are used to record the synchronization events. Okay. This diagram illustrates how TSan works. It seems to what the MSan does. TSan runtime library at the bottom implements a TSan algorithm and a set of functions that are used to record memory access events and synchronization events. Also, TSan runtime library should detect the date race by this event, recording event. All the memory access event and synchronization events generated by the application are intercepted by a TSan library. With this framework, the instrumented application by TSan can detect date race during runtime. Okay. Let's take a look at this simple demo about MSan. The main function will call the star racer function, and the star racer function will use Go racer to start a Go routine. Go routine is something like a thread, but it's not a real thread. In Go routine, it will call a store function to write x with 42. And in the main function, subsequently, another store here will write x with 43. Because this write event have no happen-before relationship, and also there is no lock to guarantee the ordering. So that would be data race. We tried. Oh. It's not clear. So the screenshot shows that the compiler how to compile this code on the left side. It used the compile option raise to compile this code. It means that Go compiler will instrument this application with TSan. And if we run this binary generated by Go compiler, the data race will be reported. So this is a demo for simple demo for how to use TSan in Go. Okay. Make summarize. MSan is a dynamic tool that detects the use of uninitialized memory. And TSan is also a dynamic tool that detects the data race. Using Go compiler to instrument MSan and TSan into application is just one use case. Obviously, TSan and MSan can be instrumented by another compiler. If you are in trouble debugging these two types of issue, hope my introduction be helpful. Okay. Any question? Okay, please.
Were you able to find any bugs in like common Go libraries? And if so, can you talk about them a little bit?
Sorry, can you repeat that?
Using MSan and TSan, were you yourself able to uncover any bugs in common Go libraries, like open source Go libraries?
Yes, it can. Because Go compiler will compile all Go library by instrument corresponding TSan corresponding detect function into that library.
And do you need to do? What do you actually need to do to turn on this sort of thing? So if I just download Go now, what do I have to do? Do I have to build compiler RT? Do I have to point Go at various libraries?
Oh yes, you just need to download the Go and use it to compile any Go application.
So it's bundled compiler RT.
Yes.
With it. Okay,
yes.
That's excellent.
What is the runtime overhead of enabling these debugging tools? What cost are you paying in performance from enabling these?
You mean the performance?
Yes. What's the performance overhead?
Okay. It was 20% slower than before. I didn't compare this result with that without using this debug tools, but I read from some paper, and it will be about 20% slower than
And that would be for each of MSan and
No.
TSan?
For MSan, it's about 20% slower than before. And for TSan, it's about 15% slower than before.
That's not too bad, actually.
Yes.
Not as bad as I thought it might be.
Yes.
Yeah.
MSan is good designed than other similar tools. I like the wing green. Do you know this? That's a dynamic tool to detect the use of uninitialized memory, but it is designed very badly.
Okay, thank you.
Okay.
Could you go back to your first example in, for MSan?
Okay.
Yeah, this one. It was not clear to me when you call the Go make int 3210, the memory will be initialized?
Yes.
Zero
Yes.
based.
Yeah.
So Go will always commit the memory.
Be
using-
initialized.
Okay, so it's basically a map with a memset or something similar inside Go,
Yeah.
right?
Yeah.
So if you do not call the C functions, the MSan won't accuse anything, right? It's just because you're calling C functions that MSan is able to see unutilized memory. That's correct then. It's only because you're calling the G function that it's actually seeing non-initialized memory.
Yes.
Okay, so, and you just use the C support, the Clang support for MSan, right?
Yeah. Yeah.
Okay. You don't, you do not do anything special inside Go itself.
Yeah. We have to how to say implement some assembly code to port the TSan library into Go, because Go controls everything on like the assembly, like all the library, all the assembly code. So for each arc, we have to implement the corresponding API to call MSan library.
Yeah, I'm asking this because when I implemented the MSan support for ARM64, I used that trick to support multiple VMAs. Because different from x86, you have 39, 42, and 48 VMAs. And
Yes.
it adds some overhead to ARM64 port. And one option would be to just support 48 VMA and reduce some overhead. And it will probably require change the way you calculate the shadow memory. And my question is what's gonna be needed to adapt Go to a new shadow memory transformation formula?
Actually, MSan just support 27 virtual memory size now. Yeah, 47.
Yeah, yeah.
Okay. For others configuration for virtual memory size, it does not support right now.
Okay.
Has all of this code landed in the upstream and been included in a release of Go?
It have been released in Go.
Okay, good. Congratulations. And what now you've done that, what's the next thing that you're looking at or interested in?
Sorry.
So it seems that this is concluded, this piece of work is finished, and MSan and TSan now behave the same on ARM as they do on Intel. Is that accurate?
Yeah.
And so what are you going to do now? What is the next task?
So you mean what we will do next for MSan TSan?
Or is it finished? Is it complete? Feature
Yes,
complete?
it's complete, finished. Okay. Any question? Okay. Thank you all for coming again. Okay.